Welcome to lesson 14. In this lesson, we're going to examine, very much in brief, certain aspects of the rheology of polymer solutions. To start with, we're going to look at how the equilibrium behaviour of polymer chains depend on their external chemical environment. This is important for us because the behaviour of polymer chains directly affects the macroscopic rheology of a solution. So we're going to examine some images, and the images that we're going to examine result from changing the pH of the chemical environment. But we're going to relate these observations to something that rheologists are going to be caring more about, which is how polymer behaves in different types of solvent. And it provides a really nice visual link to illustrate. We're also going to define three distinct categories of polymer solution, and we will see that these classifications depend on both the concentration of the polymer and on the molecular weight of the polymer. However, before we do this, let's just remind ourselves what polymer chains are and have a look at some really, quite frankly, amazing images of some real polymer chains. So, you may well remember from previous courses that polymers consist of monomer building blocks. These monomer building blocks are repeated to form a very high molecular weight chain. So in terms of an example, I'm going to pick poly-2-vinyl pyridine. The reason why I'm picking poly-2-vinyl pyridine is because that is the polymer that we're going to see real images of. So I've put on the board here two things. The first is the repeat unit for poly-2-vinyl pyridine. It's an aromatic ring with a nitrogen group substituted into it on a carbon backbone, and also an image of several repeat units formed together into effectively an oligomer chain. And the real polymer chain will have many hundreds, if not thousands, of repeat units attached to each other. Now, the images that I've just put on the board are frankly remarkable. They were taken nearly 20 years ago, back in 2005, by Reuter and Minko. And if you want to learn more about their techniques and how they did this, I've put the link to their paper in the Journal of the American Chemical Society there for you to go and have a read. So we can see in that image a scale bar of 25 nanometers, which gives a very good idea as to how small these chains are. And we can also see these chains are kind of randomly configured. Imagine that you've got a big electrical cable and dropped it on the floor and scattered it out. You might expect to see something similar, or a rope, or some shoelaces. The chains are sort of flopped down and coiled and taken on a particular conformation. What this paper does is explore how the polymer chain conformation changes as a function of the external chemical environment. The authors looked at the conformational changes with respect to solution pH. We're going to have a look at some of those images in a minute, but what we're going to do is to relate the changes they observe in solution pH to the sorts of behaviour that we know happens in different types of solvent for polymer. And that's of real relevance to us because we're talking about polymer solutions, and these are solutions of polymer in a solvent. And what we will see is a type of solvent very much affects how the polymer behaves, which in turn will affect the macroscopic rheological response that we measure and observe. So let's see what the authors found in terms of polymer chain behaviour. Their first image was taken at a pH of around 3.9. I've put a picture of it there on the board. The scale bar at the base there is 100 nanometers, so we've zoomed out a little bit. And what we can see here are polymers are liking their external environment. There's a good deal of interaction between the monomer and the external chemical environment, and the chains have opened out. They're not linear by any means, but they're certainly not coiled. However, if the pH of that external chemical environment is increased ever so slightly from 3.9 to about 4.05, there's less interaction between the monomers and their external chemical environment. The monomers start preferring interacting with themselves, and so rather than the chains being opened out, they become somewhat more compact. That effect is accentuated if the pH is raised further, and the polymer chains effectively become globular. And we can see between that first image and that last image, all we've done is change the pH by 0.25, and we've gone from nice open polymer chain conformations to very tightly coiled polymer chain conformations. And the rheological response of the solution at a pH of 3.9 and at a pH of 4.25 are going to be very, very different from one another. It is just a very small change of that solvent environment. Now, what we're going to do is to relate the observations here to what is qualitatively happening with polymers in different types of solvent. And when we look at polymer solution rheology, you will see that solvents are classified in a number of different ways because they affect the polymer chain conformation in a number of different ways. So if we take the images of the polymer at pH 3.9, what we're going to do is relate that to the notion of a good solvent. Generally speaking, in a good solvent, monomers, the chemical groups that make up the polymer, the monomers prefer solvent interaction rather than monomer interaction. And so the chain opens out as all the monomers try to get exposed to more solvent. At the other end of the scale, and this relates to the images in the paper at a high pH, at 4.25, you can find poor solvents. And in poor solvents, monomers prefer other monomer interactions compared to interacting with the solvent. And that is where you get this very globular behavior and these very, very compact, tightly coiled polymer chains. The monomer really doesn't like the external chemical environment and wants to interact with itself. In the middle of these two extreme behaviors, we find a behavior where the monomer-solvent interactions are effectively cancelled out by the monomer-monomer interaction. So the polymer chain takes a conformation as if there were no interactions with anything. And this is something that you hear called theta solvent behavior. And it's an almost ideal chain conformation. So when you read the solution rheology literature, you'll hear good solvents being mentioned, poor solvents being mentioned, and you'll see a lot of reference to theta solvents because it gives the polymer the ideal chain conformation. And you'll see that there's various numerical measures of solvent quality, and we will come across some of these later on in this lesson. So the key take home here is that the interaction between the polymer and the solvent is really important. We've got this measure of what we call solvent quality, and that solvent quality strongly influences the polymer chain conformation, and that polymer chain conformation strongly influences the macroscopic rheology of the solution. So we need to be aware of different types of solvent, and we need to be aware of different solutions with different concentrations. So let's have a look now at concentration dependence on polymer solutions. We're going to start by thinking about dilute polymer solutions, and we're going to look at dilute polymer solutions in the context of a good solvent where monomers like solvent interactions. We can imagine this in our mind's eye to look a little bit like this. You've got open conformation polymer chains because the monomers like the solvent, and if we draw a dotted circle around the polymer chain, we can define that, if you like, to be an extent of the space that chain is going to occupy. A dilute solvent, a dilute solution, is where polymer chains are effectively non-overlapping with other polymer chains. You're essentially looking in the rheology at polymer-solvent interactions. Now, there's a very useful parameter, C star, the critical polymer concentration, that we can use to demarcate whether we're a dilute solution or something else. We're going to discuss how we estimate and calculate C star later on in this lesson, but for now, dilute solutions are where the concentration of polymer is a lot less than this critical polymer concentration C star. So, what can be very, very useful is once you know what solution regime you're in, is to be able to have some kind of estimate for an aspect of the rheology. So let's look at an estimate of the shear viscosity for dilute polymer solutions in good solvents. So there on the board is a cartoon of my dilute solution. The chains are nice and open, so therefore it's a good solvent. And we're going to define a quantity called the intrinsic viscosity. Formally, the intrinsic viscosity is the solute's contribution to the solution viscosity. So in this case, it's how the polymer affects the solution viscosity. We can relate this mathematically as follows. My intrinsic viscosity has a symbol of eta in square brackets. That is equal to effectively a ratio, which is the solution viscosity less the solvent viscosity, divided by the solvent viscosity multiplied by the polymer concentration, but the intrinsic viscosity is in the limit of the concentration going to 0. If we look at the units of intrinsic viscosity, we can see that the Pascal second terms of the viscosity in the denominator and numerator of that quotient that has been taken the limit of cancel out. And so the units of intrinsic viscosity are those of inverse concentration, whatever we happen to have measured our concentration in, grams per mole, grams per cubic meter, whatever. As a slight aside, one way we can estimate C star is it's the reciprocal of my intrinsic viscosity. We'll see a way we can experimentally determine it later on in this lesson. So that's the intrinsic viscosity. Now we can use the intrinsic viscosity to get a measure of the shear viscosity. And so it's a two-step process. Firstly, we need to be able to estimate what the intrinsic viscosity of a certain polymer solution is. And there's the Mark-Halvink equation we can use for that. And the intrinsic viscosity is equal to the expression that I put on the board. And that expression involves the polymer molecular weight. It involves a measure of the goodness of the solvent. So here the power A is a half for a theta solvent and around 0.8 for a good solvent. It'll be less than a half for a poor solvent. We also here have a constant, the Mark-Halvink constant, script K, and you've got tables of Mark-Halvink constants for different polymers and different solvents, and so that can be looked up. Once we have the intrinsic viscosity, we can work out what the solution viscosity is, and there are a number of equations out there for dilute polymer solutions. I've chosen one of the original ones, which is the Huggins equation, and on the left-hand side of the Huggins equation, we have the solution viscosity, eta, being in a quotient with the solvent viscosity. So the left-hand side reads eta minus eta s over eta s, but we can rearrange that such that we just get the solution viscosity eta. On the right-hand side, we can see that we need to know information about the intrinsic viscosity, which we can calculate from the Mark-Halvink equation. We need to know something about the polymer concentration, and we need to know a Huggins constant for the particular polymer solution that we're looking at. Okay, so that's dilute solutions. If we add a bit more polymer, we move into a different regime. If we add more polymer, the polymers probably start to impinge on each other a little bit. And this is the regime that we call the semi-dilute regime. Again, the images I'm showing are for a good solvent, the polymer chain conformation's nice and open. And our semi-dilute polymer solution is where we get the space that a chain could occupy, those yellow dashed circles, overlapping with the spaces that other chains could occupy. And so in effect, we have polymer coils starting to overlap one another. This happens when the concentration of polymer is roughly equal to the critical concentration of polymer C star. So, what we find is that if we've got a high molecular weight, the way in which these polymer coils overlap one another can result in these coils getting tangled up in one another. Imagine you've got a big bag of rope and you chuck it on the floor and all the different bits of rope overlap one another. Sooner or later it's going to end up in knots, you can guarantee it. And so that, if you like, is an image of entanglement. Chains don't entangle if they're nice and short. So in the semi-dilute regime, you've got a molecular weight dependence on whether this tangling phenomenon happens. And the reason why we care about this tangling phenomenon is that it really greatly alters the macroscopic rheology. Entangled polymer rheology is pretty complex. Unentangled rheology is still complex, but a lot simpler. And so for an unentangled system, we can estimate the viscosity via something called the Martin equation. Eta here again is my solution viscosity, eta S is my solvent viscosity, C is a polymer concentration, and capital K subscript M is something called a Martin coefficient. And again, there's tables of Martin coefficients that we can examine in order to get a viscosity estimate for a particular polymer solvent system. So let's add a little bit more polymer to our polymer solution. Now we get a point where the chains really are overlapping a lot. And what happens at this point is that there's less and less solvent around the polymer chains. And so the polymer chains can't open out as much to interact with the solvent. They're interacting more with themselves. So the polymer chain conformation starts to contract. And it will contract as far as it would for a theta solvent, assuming that it was in a good solvent in the first place. This is something that we call the concentrated regime. And the concentration of polymer in the concentrated regime is greater than that critical polymer concentration C star. Again, if we've got very long chains, very high molecular weight chains, the chances of the chains tangling in one another is now a lot higher. And so concentrated polymer solutions are far more likely to be entangled. But entanglement doesn't have to happen for concentrated polymer solutions if you've got lower molecular weight polymer chains. So at low molecular weight, you may still have concentrated but unentangled solutions. So let's summarize these concentration regimes in terms of a map. And this map is taken from an early publication by Gracely. What I'm plotting here on the x-axis of this map is the polymer concentration. And on the y-axis, I'm plotting the molecular weight of the polymer. And we start off with the dilute regime. For very, very, very low polymer concentrations, the dilute regime will happen for all molecular weights. Remember, the dilute regime was one where the polymer coils don't overlap one another. And so the shorter the polymer, the less likely they are to overlap, so we can have more of them in there and they still won't overlap. The longer the chains, the more likely they are to overlap. But if we have very little long chain polymer present, they still won't overlap. So that explains, in terms of a mental image, why there's this molecular weight dependence. The next regime we saw was for an increased concentration of polymer, and that was the semi-dilute regime. And so that falls into two categories, semi-dilute and unentangled, which is the light green. But for higher molecular weights and higher concentrations, we can see these polymer chains starting to tangle up in one another and greatly affecting the macroscopic response. And so we end in the semi-dilute entangled regime. The third regime that we saw was a concentrated polymer regime. And again, this splits into two components. For low molecular weight polymers, you can have a regime that is concentrated and unentangled. But for higher molecular weight polymers, you end up in a regime that is concentrated and entangled. And there's a far higher likelihood of entanglement with increasing polymer concentration in the concentrated regime. So, one final footnote. We have discussed a lot C star, that critical polymer concentration that we can use to demarcate whether or not we're in the dilute, the semi-dilute, or the concentrated regime. We saw a way of estimating C star. It was a reciprocal of the intrinsic viscosity. We can also experimentally determine C star. So the graph that I've put on the board here is a plot of the solution viscosity on the y-axis as a function of the weight concentration of polymer on the x-axis. And you can see that the chemist who has done this has spanned a very, very wide range of polymer concentration, almost 5 orders of magnitude. What we see in this plot are two regimes of behaviour. And so we can see that there's sort of a power law behaviour at low concentration, that's the blue dashed line, and a different kind of power law relationship at higher concentration, the yellow dashed line. And it is the intersection of these two power law regimes that gives us C star. So that's one way that C star can be found experimentally for a given polymer solvent system. So let's summarise. We've seen with some remarkable imagery, that the polymer chain conformation depends on the external chemical environment. The external imagery concerned the pH of the external chemical environment. We're more concerned about the chemical nature of that environment, in terms of it being a good solvent, a poor solvent, or a theta solvent. And we saw that for good solvents, monomers like solvent interactions and chains open up. For poor solvents, monomers prefer monomer reactions over solvent reactions, and the chains become globular and very, very tightly coiled. And we have the crossover between those two where there's no external or internal influence on the polymer chain conformation, and we call that the theta solvent. We saw different types of polymer concentration regime, and we classified them into dilute, semi-dilute, and concentrated. And we also saw that for the two latter categories, the semi-dilute and concentrated regimes, depending how long your polymers are, how high the molecular weight is, you may have the polymers tangling up in one another, becoming entangled, or if they're low molecular weight polymers, nice short chains, they're unlikely to become entangled in one another. We also saw for the dilute and semi-dilute regimes various methods of solution viscosity estimation that we can put into practice in daily use.